thank you everyone for joining this first structure seminar of the term and of the year. Our first speaker is Professor Alan McRobbie, who very kindly agreed to me volunteering to him giving the first seminar, and his talk is on graphic statics, and it looks pretty fascinating. So Alan, the floor is yours.
Thank you, Jamie. Well, yes, I was only asked to do this less than a week ago. There was no speaker for our first session, and I really believe in these structures seminars. I think they're an important part of what it means to be a structures group, and I'm really glad that one of my colleagues has come along to these. But I'm reminded of when I came to one of these about 15 years ago, and there were two students, they shall remain nameless. One was called John O, let's just call him John O, and the other was Wesley W. And they gave two talks as they do at the end of their PhDs. You give a talk about your PhD. So John was doing masonry structures, and it was all about cracking in buttresses of masonry structures. And Wesley was doing wrinkling of membranes. When you put them into shear, they get these wrinkles. And it kind of became clear to me that at the end of this, that both these were identical talks, but with the signs reversed. Because one was a pure compression field and the other was a pure tension field. And so everywhere John had a crack, Wesley had a wrinkle and things. And the beauty of it was they hadn't spoke to each other for the whole 3 years of their PhDs until this final talk. And I kind of thought this is a real failure here of us as a group getting together. So the cowboys and the farmers should be friends, and we should all come to the structure seminars, even if it's not in your area, because I think you'll learn things that may be in your area. So I'm going to talk about graphic statics, which does actually cross a lot of areas. It's got this title, Graphic Statics as a Legendre Transform, and this is an advert for those watching it on the recording, because we can't see any fourth years here, but do come along to the course that Bill gives, the module Advanced Structural Design. Bill's put this together with the help of Petcha. It's a fantastic new module, and actually postgrads can come along and postdocs can come along to this. Jamie did it last year, a fabulous, totally different way of thinking about structures that Bill's put together. And it's a brilliant course. If this talk is rubbish, my talk is rubbish, it's no reflection on Bill's course, which is fantastic, okay? So don't be dissuaded anyway if you don't like my talk. I'm just going to talk about one or two few areas on that slide there. So 4D2, it runs starting in January. So today's talk, Introduction to Graphic Statics, I'll just tell you what it is in case you've forgotten. Some recent research, some preliminaries in the maths, then I go into Maxwell's diagram of stress moments, as it says there. So that's the layout for the talk. And the graphic statics, so it was invented hundreds of years ago, and you can use it for designing roof trusses and things like that. The architects learn how to do it this way. We don't teach engineers how to do it this way as a general rule. You can do it with a ruler, generally. You start a pencil and a piece of paper and a ruler, and you start with a structure and you draw the form diagram and the force diagram, and you can go from one to the other just using a pencil and paper. And so here, let's do it ourselves. So we're going back almost 500 years there, no, 300 years, sorry, to Varignon, form and force. There's the form diagram, it's some weights hanging on a string, and there's the force diagram above. And let's focus in on that node Q there. Can you see my mouse? Yes, the node Q. So you know from your school days that there's a polygon of forces for equilibrium there, and that polygon must close to get equilibrium. So we just look at that node Q. The three forces that meet there can be rearranged to form this closed polygon like so. So that's the sort of basis of graphic statics. And if you look, we can then start to connect other polygons together, because when it's on the node P, it will also contain this member here, which is that member there. So we can then draw P next to it. We can connect them together to make a larger picture where all these polygons are joined together, and that's the force diagram. The thing you want to notice is there's a duality here between a node and a polygon. The node Q, there's a sort of duality to that with a polygon. And the way I drew it there, I drew the lines parallel. There's also a duality between the lines. A line in this diagram has a corresponding line in that diagram. And when I drew it, I drew them parallel. Throughout this, we're going to use Maxwell's convention now, though. We're going to draw forces for lines perpendicular to each other rather than parallel. And that's Maxwell up at the top, who we're going to follow. in this. So this all started when Bill, who is on the call here, here's Bill in front of the Burj. He turns up, Professor Bill Baker of Cambridge University Engineering Department, also happens to work for a firm in Chicago. He turned up here about 6 or 7 years ago, and he basically said, read Maxwell, go back and read Maxwell in the original. There's all this amazing stuff in Maxwell. So go and read the original papers. So when the world's leading structural engineer tells you to go and read the works of, no doubt, one of the world's leading scientists, you listen to this. Maxwell is one of the absolute greats of the world. Physics in 5 words would be Newton, Maxwell, Einstein, quantum, and dark, I think. So Maxwell is at least 20% of physics, I think, with his electromagnetic theory. And he also wrote lots of papers about structures as well. So it's an absolute great. His papers on structures, it's all about the geometry of structures. And when he was working on electromagnetism, he was also interested in geometry. And the geometry he came up with for electricity and magnetism to fit the two together was so weird that it wouldn't fit in the universe. And so 40 years later, Einstein came along and said, tell you what, let's just change the universe, and now it fits. So that's how they got special relativity into the talk. So anyway, Maxwell's an absolute great. So you listen to this. So I did have a look at Maxwell, and I was blown away by just how much I did not know. As I say, you get to my age, you think you know your field. You're not being arrogant. You've just been in the field long enough. You think you know what you need to know. And I found so many things I just did not know. So here it is. This was the recommended reading. Professor Calladine has kindly read it, which is very good. Anybody else had a look at the recommended reading before this talk? This was in Maxwell's 1870 paper. In 1864, he wrote a great paper. 1870, he wrote a paper about structures, and he invented electromagnetism in the middle of those in 1865 and totally changed the universe. So quite a person. So this is Bill. Bill uses this all the time. This is Bill's notebook. If you met Bill, he walks around with a notebook and a pencil, and he draws diagrams and on his notebook, very sort of professorial, and then he goes and builds them. He's actually built these ones in North Sydney and in Chicago with this special sort of, he's optimized the bracing, the rib bracing, using these methods, and then he's kind of built it and saved, as Bill likes to say, he saved more steel. It's sort of materially efficient. The money he's saved more than pays for the design fee that the company gets, his company gets. So, so let me introduce graphic statics. That was a bit of a blurb, bit of a polemic. Graphic statics, how does it work? So you can do it with a pencil and paper, but there's another way to do it. And I'm going to teach this way of doing it using area stress functions. And you may have seen this before because I've shown it a few times over the years. But there's your structure on a plane, and it's got these 3 forces coming together. So it's sort of like a bicycle wheel that's sort of stressed, a triangular bicycle wheel with a compression hoop, triangular compression hoop surrounded by these 3 tension spokes with a triangular compression hoop. And what you do is you raise that up to make a polygon. You take hold of that central node and you lift it up in the air and you make a pyramid. You then shine surface normals, you shine laser beams off each of those faces, and all of those laser beams come from some arbitrary point on the base plane, and they're the surface normals, and there's one from the original plane as well, so there's 4 surface normals, and you intersect those with what's called the reciprocal plane. So this might be at z = 1, if you like, and it draws 4 dots up there. And you can already see the duality. We're going from a plane to a dot. But we now connect those dots, and you've drawn the reciprocal figure there, like so. And you found the forces. So without going to a matrix or a computer or writing any Greek letters, you've actually found the forces in your system. It must all be in these proportions, just using geometry. So the force in bar B is proportional to the length of the line in the force diagram up there. So it's all done without matrices, which is rather fabulous. So the construction of normals is the same as plotting the gradients, because later, instead of drawing normals, I think in terms of the normals and the laser beams. That's how I think, but actually you should really think in terms of the gradient of those faces, and that actually points in the opposite direction. It's exactly the same size, but it points in the opposite direction. So here you can see we've got the gradient, 1 is to m, and here we've got the normal in the proportion 1 is to m. So it's the same m, the same slope, but instead of pointing that way, I should actually point with the gradient points that way. So if with my laser beams, always give my diagrams inside out, but don't worry about it. It's just a factor of -1. Because gradient's going to become central to this whole story. So here we are, it's the gradient of the red face. It's actually the negative, but forget the -1 for now. The gradient of the red face is that vector there. So there's a duality, planes map to points, and the gradient defines the mapping of the key takeaways. If we know the gradients of our pyramid, we can draw the reciprocal. And also lines map to lines. So that red line, because these two map to these points, and so the thing that connects the 2 points is the thing that connects the 2 areas. So that white line is dual to that red line there. And if you look down on it, they will be perpendicular to each other, which is the Maxwell convention. So here's a quiz for you. That was just a quick intro. For what geometries can this truss sustain a state of cell stress? If I were to tighten this bar in the middle, would it stress up or would it move? For what geometries will this work? Can you work that out? What conditions? Okay, how about this one? For what yield line geometries can this slab collapse? Let's do a concrete one because we've got concrete people here. What are the conditions on the geometry for this to be a compatible yield line collapse mechanism? It's simply supported all the way around. And the answer is, and you know this from your yield line collapses, that those 3 must meet at a point because these things have to stay as flat areas. And so this flat area and this flat area, they form like a pyramid and they must meet at a point. So you know that one. So there it is there, those flat areas must meet at a point. And the point is, it's exactly the same in the truss. It's exactly the same analysis there, that those hinge rotations on the left must add to 0 and the bar forces. So the thing on the left is a yield line collapse of a slab, and this one here is a truss, a pin jointed truss. And the bar forces must sum to 0 and they must all meet at that point. So for the truss to work, it must be the 2D projection of a 3D polyhedra with plane faces, which is like your yield line collapse mechanism. So it's exactly the same mathematics. So if you're working on concrete slabs, which we had a whole group with Cam Middleton, etc., and Paul is here. Yes, as Paul was working on these collapse mechanisms, you could have modeled them as a truss instead of a collapse mechanism, and it would have been the same. So Steve Denton, I think, did I say that on the previous page? Yes, Steve Denton's PhD pointed out this similarity between trusses and yield line fans, yield line collapse mechanisms. It's the same problem, basically. So here's another quick one, just to show you've got it. External loads. So we've got external loads this time. So this really is a bridge with some external loads. How do we deal with the external loads? Well, we add a follicular below it, and now we've got a closed system. So now we can do what I just said. Let's label the areas, pull it up into a polyhedron, stick the laser beams on. Each face points out a laser beam. It draws these laser beams like that. You connect the dots and there's your force diagram. You've got the forces now in that loaded truss. So for example, the force in bar AB is up there and the load W is that length there. So you've worked out the forces in your structure without doing any matrices or anything like that. You just did it all with, rather amazingly, you drew your structure and then you tipped it into the 3rd dimension. So try this when you get a job as a structural engineer. So to your boss, you draw the bridge and then you do a bit of origami, fold your diagram, and then you've worked out all the forces on it without using any computers. So that was a quick intro to what graphic static is, how it works. This is some recent research. So I've been working on this since Bill arrived, with Bill and with various other people, some of whom are here. And this is just an overview of some of the things that we've done. We got the this Maxwell-Minkowski diagram, which is rather cool. So you can flick between your form and your force, or your force or your form, like so, or we can even do it in 3 dimensions, like so. This was originally proposed by Zanny and Pennock, but I didn't know that when I invented it. So it was actually invented before me by those, but they didn't do it in 3D. But these are rather cool. I've never seen bridge design looking quite so cool as that before. So I rather like those. And it tells me almost everything. It tells me Maxwell's load path theorem. It tells me all sorts of other information. I mean, I can give a talk on almost every one of these slides for an hour, but I'll just. So you can also use that for finding strut and tie fields within concrete. Marina's written, my student Marina, who is here, PhD student now working at Foster's. This is from her work. So you can do strut and tie models using, and it is the Maxwell-Minkowski diagram, which is the addition of your form and your force diagrams, gives you the stress field. We can do kinematics as well, not just equilibrium, and this was work I did with Georgios and also Marina and Laura, and we can also do 3D kinematics. So this is Marina working on Rhino. So this should actually do something. You slide the pieces of your force diagram around and it tells you how your form diagram can move. So you can find the mechanisms of your tensegrities by this method. So you can, for example, there is a mechanism on this icosahedron that can be identified this way. This is just a whistle-stop tour of some of the things we've done. We can now add moments as well. We don't just do trusses, you can do 2D moments. This was a paper with Chris Williams. And I can now even do 3D moments with axial and the two shear forces and the torsion and the two bendings. And you get lovely diagrams like this. And I wrote this all up in a paper. And not many people like this. They think it's a bit too complicated. But the punchline was the equations for this came out like so, F plus E naught M in 4 dimensions, and it's exactly the same as the 6-component stress tensor. Stress bivector is the same as the electromagnetic bivector. So if you don't like it, I think Maxwell would have liked it. I think this is what Maxwell was looking for. Chris Calladine often said to me that when Maxwell was trying to play with form and force and all these concepts of duality, it's because in the back of his mind, he wanted to get electricity and magnetism together. And it turns out it isn't form and force, isn't the similarity between electricity and magnetism. It's actually force and moment are the two things that have the parallels. But that's rather interesting, I thought. And we've since moved on to graphic stability. This was Cam Miller, did this as his 4th year project. Cam's on the call here. And we just had a paper, just appeared today apparently, about Robert Myart's roof in Chiasso. It's a very famous roof. It's just a small shed, but very famous. There's no diagonal bracing on it. And I always tell my students, don't do this, put the diagonals in, please. But he left them out and it's very, very economical. And we could study the stability of this, not just does it, can it carry the loads, but via equilibrium, but is it stable to small perturbations? So we could do that. And I've since moved on and doing grid shell design now. There's lots of different avenues. I'm working on this with Giancarlo, who was here online. So yeah, he's there, part-time PhD student working with Arup, working on those. So those are just some of the things. So that's it. So now I'm going to get on to what this talk was about, to tell you some of the things I learned that I didn't know before I started looking into Maxwell. So projective geometry, I didn't know anything about projective geometry. I thought it was something we did in the DPO, but it's not. It's a really deep mathematical subject. And it starts off with some concepts. Let's do 3D projective geometry. We have this duality. Duality is central to projective geometry. A point is dual to a plane, a line is dual to a line, and a plane is dual to a point in projective geometry. By which I mean you can swap the words point and plane in any theorem in projective geometry, and it is still a true theorem. Put your hands up if you already knew this. Danny did. Yeah, I've told you recently. Well, fair enough. That's all good that you did know this. So we can swap the words point and plane are the rules of the game. And so 3 planes define a point. You all agree with that? Swap the words. 3 points define a plane. Yeah? How about this one? 2 planes define a line. What's the dual of that?
2 lines define a plane.
No, Chris, it's not.
No.
No, that's the trick question, and you found it, Chris. No, it's you only swap the words point and plane.
Oh.
So 2 points define a line.
Oh, yes.
Yes, no, it's there for a reason to catch someone, and thank you for doing that. But it's deeper than this because you get, for example, Pascal's theorem and Briançon's theorem. They're the same theorem, but we're just with the word swapped. And famously, Cremona, I think it was, wrote the book about projective geometry in 2 columns. where in one column it was points and planes, and in the other column it's planes and points. And he just wrote the whole book like that because of this wonderful symmetry. Now, I didn't know any of that. It's rather beautiful. We will actually use that a lot as we go. So here's another concept now, it's called the polarity. And this is the way Marina does her graphic statics. If Marina's still here, she is. This is how she does hers. This is how we go from points to plane. You have this thing called the paraboloid revolution. It's all in Maxwell's 1870 paper, a paraboloid revolution. You pick any point, and then you take the tangents to this paraboloid revolution, and they define a ellipse, and that ellipse defines a plane. So if I give you any point, you now get a plane. So polarity is a mapping from a point to a plane. So give you a point, and I can give, you give me a point and I'll give you a plane. So you give me a point, like all the points on these tetrahedra, I can then draw all of the planes and they will define another tetrahedra, the dual tetrahedron up there. And then you project them down and you've actually got the Maxwell 1864 figure 1. And there's the three-pointed wheel and there's its dual up there, the force diagram. So that's a rather, I think it's much easier to do the laser beams. Yeah, the laser beams make much more sense intuitively than trying to say tangent cones of paraboloids. But anyway, that's how Marina does it. And it's very efficient and you can code it all up and do it all in Rhino. So the last thing I want to introduce is what's in the title of this talk, Legendre transforms. You may have met Legendre transforms. They're used in mechanics. If you've ever done any hard mathematical mechanics, to transform between a Lagrangian and a Hamiltonian formulation of particle mechanics, say. So I've met them there, and they're also used in thermodynamics. If you remember your thermo stuff, you had all of these thermodynamic potentials, internal energy, entropy, Gibbs free energy, Helmholtz free energy, and you transform between those with Legendre transforms. So what is a Legendre transform? Here's a line, it's a curve. And the way you would normally define this curve is, say, f is a function of x. If I give you a whole set of x's, I can then give you a whole set of f's, so we can plot them all. So there's a sort of correspondence between the x's and the f's. And so it's the set of all x's and f's defines the curve. Instead, I could, to define that point, I could tell you the intercept here, which we're going to draw minus g. I'm going to draw a line at a particular slope and draw that. And if I draw the set of all of those lines, the envelope of those lines will draw the curve for me. So I can use this really sort of slightly funny way, it's called the Clerk coordinates of a curve, and define it in terms of slope and intercept, negative of the intercept, but the intercept like so. So here it is here, I've drawn the geometry a bit more carefully. So here's the point F, this is the x-axis, so here's the point F. This one is minus g, so there's f and g, and because that distance is x and the slope is k, we've got f plus g must equal kx. Yeah, so you would all agree that f plus g must equal kx, just from the very, very simple geometry. And that is the simplest Legendre transform in one dimension. And we can generalize this to two dimensions. We have a more complicated surface, so we draw a plane, but it's now got two slopes, if you like, the slope is a vector. So it's got two components, but it's still got the one intercept, where the plane intercepts that axis. So the transformation from fx to the gk coordinates is a Legendre transformation. It is defined by k is the f by the x. So k is my coordinate, and it is given by the slope. So this is the key, that the coordinates are given by the slope. And then the intercept g is given by this, because we knew that f plus g equals kx, so stick the f on that side and you've got it. It's very simple mathematics. And if we go to higher dimensions, you've got k is grad f, the gradient, the slope of the function, and instead of doing k times x, you do k dot x, because you've got more coordinates, and you still subtract the scalar f, the intercept. So that's the maths of a Legendre transform. And the way to remember it is it's really easy. Linear, y equals mx, nice and linear. If you want to add y equals mx plus c, that's a straight line, but it's called affine rather than linear because you've got the c. And if you want to be really classic, take the c, change the sign and stick it over on the other side. Same equation, you've got y plus c equals mx. And now this one has an unbelievably beautiful symmetry because we've got two things are added over here, two things are multiplied over here. We've got the c's in the end, and the X's and the Y's, and we can sort of swap them. There's a much more beautiful symmetry in the mathematics there. That's the Legendre. And in higher dimensions, you got the sum, F plus phi. Instead of calling it G, I've called it phi this time. And that's equal to, instead of calling it K, I've given it these letters. And the reason is there's a duality in the Greek and the Latin here, that the Latin letters F, X, Y, Z, to dualize it, you've got the Greek letters phi, psi, theta, like so. So note the duality. That's for 3D. If it was just 2D, you drop this one, and if it's just 1D, you drop that one there. Okay, so this is what I found when you look into Maxwell's book. You find this thing called a Maxwell diagram of stress. Now put your hand up if you've ever seen one of these before. Chris Calladine has. I'm looking on screen. Maybe Chris Morley's going to put his hand up, but no, so no, he hasn't. So no one else here has seen them. So this is one of the things you find, and this is in Maxwell's 1870 paper, and it's for a beam. So this is basically Euler-Bernoulli beam theory, like you've never seen it before, except Chris Calladine has seen it before. So let's have a look how it works. So what he defines in this 1870 paper is a really weird thing about this thing called the stress space. And I've worked with stress functions all my life. I know how stress function works. You take second derivatives, and it tells you the stress field. But I didn't know about this stress space until I read it. Bill made me read it. And the way it works is that there's this is your actual space. So over here, so this is your body. So let's imagine it's a plate under stress or whatever. And you draw any line across your plate, or this section of the side of the beam or whatever. And the forces that are acting on that are reproduced over here. There's a mapping from that curve A to this curve alpha in this fancy stress space. And within this stress space, there's only isotropic pressures. Very simple, idiotic. P is the same in every single direction. I'd call it hydrostatic, but it's even simpler because it doesn't vary with depth. The P is just the same every direction. And within this space, if we do this mapping right, we can reproduce any stress distribution here within this incredibly simple one. So this is really hard with shear stresses and normal forces. Everything's varying. Things are varying in direction, everything. But over here, we can completely reproduce it very simply. So that the force FA is equal to the force F alpha over here. And it instantly follows from that. Well, hang on, there's a duality going on here. The curve is going to the curve, a point is going to a point at the moment. We're not doing a projected geometry. Pick a point over here and it maps to a point over there at the moment. If I have a closed surface, it instantly follows that because the forces are the same, over here the forces must be in line by hydrostatics. And so over here, we know that they've got to be equal from the definition, but they might not line up. But so far we've not said that they're going to line up. So there may not be moment equilibrium. We haven't guaranteed that yet. But Maxwell will go on to guarantee moment equilibrium. And the way he guarantees moment equilibrium, he says, pick any function over the body. So pick some function f of xy, which we're going to call a stress function, the area stress function probably, and let a point in the body space be mapped to the point in this funny stress space with its isotropic pressure by this mapping, which is the gradient. Take the gradient of that one and just plot it over there as a vector, as a point, the dot there. And if you do that, the coordinates in the stress space are given by the gradient of the stress function. There is another function we can define, G, over the stress space. So F is over my body space, G is over this space, and we can define G by this formula here, which you can spot as the Legendre formula. Stick the F over on that side, you've got the Legendre formula. And we're going to call G the dual stress function. And Maxwell shows that we can map back from our dual stress function by taking slopes. So dg by d psi and dg by d eta will define the x and y that you started with back over there. It's an involution. It goes back and two between these two things. So the gradient of your dual stress function gives you your coordinates back in the body space. So let's have a look at Maxwell. He shows these mappings guarantee not only force, but they also guarantee your moment equilibrium. So let's try it on a beam. So there's Maxwell's beam that he's drawn. He's drawn these funny ends on it because he wants to He's worried about the end boundary conditions. I'm not quite so worried about them. So I'm just going to think of a really simple stress function. This is the stress function for Euler-Bernoulli beam theory. Doesn't satisfy the biharmonic equation if you look in detail near the supports, but don't worry, that's in 3C7, I believe, as an example paper question. So there's the beam, and I've drawn some coordinates on it. It's got a UDL, it's supported at the end by these end shears, sort of parabolic end shears. So it's going to be pure Euler-Bernoulli beam theory. It's not supported or supported. Supported by these end shears like so, and it's all in equilibrium. Just draw a stress function over it, and I pick this stress function here. Quadratic in the x direction, cubic in the y direction. Now, what would I normally do with a stress function? You take the second derivatives and you plot the stress field. So this is what you normally do with a stress function. Take the second derivatives. There's the formula at the top of the area stress function. You take the second derivatives. You've now got the stress fields, and now you can chase these like streamlines, and you can plot the principal stress trajectories. And so this is Euler-Bernoulli beam theory for that stress function there, like so. Compression blue and tension red. Like so. So that's what I normally do. What Maxwell does instead is he takes first derivatives, not second derivatives, he just takes the first derivative. So there's my stress function, take the first derivatives. The first derivatives are the gradients. So they define over here in my sine and eta space, they define the coordinates over there. And what you get is that any line on that diagram maps to a line on this diagram. So this is Maxwell's diagram of stress, he calls it here. So pick any point you like, J was up there, J is there, J maps to that point there. Very easy to code up, do that in MATLAB, take you half an hour and you get a beautiful diagram like that. And how does it work? Remember that over in this space, we have just this total isotropic pressure P, pushing in every direction P. So let's pick a line L to L, which is over here. So L to L, what do we expect from Euler-Bernoulli beam theory? We expect to have bending stresses, flexural stresses like that, pushing and pulling, and a small shear stress because we've got that much shear pressing down that's got to be carried there. Yes, so we've got to have a load of forces pressing this way, and you can see them. Here's the forces pressing this way. Yeah, going from L to L, and here we have forces pressing that way, and here's the forces pressing that way. And we've also got to have these shears. Well, there's some shear pressing down, which are those ones pressing down. There's a small shear pressing down. And in fact, if you make this a closed loop, the total force from L to L, these ones add to 0, and it just leaves you the upward component. So that distance accounts for the shear pressing down. It should be the same as that distance there, times the load there. So this contains all the information about the stresses within the beam. And we only took first derivatives. I've taken this from Alexandra Bogini. We're writing a book about this. Well, Bill's writing a book. We're all helping Bill write a book. And Alessandro uses this diagram. And I thought it was such a clear diagram, I'd use it today. But we haven't yet drawn the dual stress function. Okay, so the dual stress function is, this is the G. So on the ground, if you like, will be the diagram of stress. And now we've also plotted this third direction, G, this dual stress function. So put your hands up if you've ever seen this diagram before. And not even Professor Caladine's putting his hands up this time. So this is kind of really rather new, except it's over 150 years old. But it's, well, actually Maxwell doesn't draw this diagram. So I've just drawn it, I've plotted the G as well here. And G is given by the Legendre transform there. So this is the dual stress function. And let's try and get our head around what does it mean. Well, let's compare with some things we know from graphic statics. So let's do a sort of Maillard style bridge. There's the form diagram over here with the UDL on top. I can draw a stress function on these polyhedral stress functions that will give me the forces in all of the bars. On this polyhedral stress function, the force diagram will look like that. We all know that a suspension bridge or an arc bridge, the dual, looks like a cable stayed bridge. So the forces are given by that. And if I now pop it up, which we never do in graphic statics, pop it up with this dual stress function, you get a diagram that looks like that, which is a sort of discrete version of that last smooth diagram I drew there. Pick a different truss. Oh, and I've superposed it here. I've actually superposed it so you can see the graphic statics superimposed on the Maxwell diagrams. So they're not very far distant from each other. It's a different structural form, but there's a lot of similarities between the discrete version and the continuous version. Pick another truss, like a Pratt truss, do it again, draw a stress function, a polyhedral area stress function, and there's the force diagram. This is what it looks like if you add this third direction of the dual stress function, and that's it superimposed. And again, not very far away from Maxwell's one as a beam for the stresses within the beam, for the truss that's carrying it. So what is this thing that Maxwell's sort of drawn here? It's a bit like we've now got a continuum version of graphic statics. We've now got continuum form diagram and a continuum force diagram. And we've never kind of done this before, really. We've worked a lot over here in the discrete version. In the discrete version of graphic statics, force diagram, it's a truss, and over here you have a force diagram, and it's also got looks like a truss. Whereas now we've got a continuum version. So when Maxwell develops the theory behind graphic statics, he actually develops everything in the continuum case, and then he goes to the discrete limit. And we've kind of forgotten the continuum bit that he did before he went off to do the graphic statics. And the mapping between the two is given by Legendre. So graphic statics is a Legendre transform, is basically the title of this talk. And there it is there. So let's have a quick look at this. There's Maxwell's method now, as you took the Legendre transform from there. And this is what I would normally have done. But now there's this whole extra side there. So there's Legendre, there's at the top. Where do these two worlds collide, these funny two worlds that you're mapping between the two? Well, I've written G as a phi now, so I really get the Greek Latin duality. These two worlds collide where they're the same. So write phi equals f, squiggle equals x, and eta equals y, your x, y, y. It's Marina's or Maxwell's paraboloid of revolution. So now this paraboloid of revolution makes sense to me what it is and what it's doing there. Is that this is where the Legendre transform, these two worlds collide along that paraboloid. So now it's got some meaning to me, why we should use this paraboloid and what it means to be there. What else can we discover in this new world? Well, the first thing I found is that if you look within that new diagram, it tells you the moments. And rather amazingly, Maxwell didn't seem to notice this and didn't write it down. Maybe he did, but he didn't write it down. He was busy writing the electromagnetism, to be honest. To give him credit, he had bigger fish to fry, probably. But anyway, the moments are all there. And the moments are given by the differences in the G, the differences in the Z coordinate, if you like, this extra dimension, the dual stress function dimension give you the moment between 2 points. So here's an example on the beam, and let's just something I can do. So here's the beam. If I pick between I and I, we all know at the moment it's going to be WL squared on 8. So on here, all the little letters are up there. So I and I, that's going to be WL squared upon 8. And if I now go from I to Q, which is from here to big I to Q, what we got? We got WL upon 2 times the lever arm of L upon 4. It's also going to be WL squared upon 8. So the distance between I and Q, so it's Q to I, the vertical distance is also WL squared on 8. Yeah, and then if we go Q to Q, which is over here, here we got W upon 2 times L upon 2 is WL upon 4. So that's the full height, for example. So all the moment information is included there. So that's one thing we can find. I can even generalize this to 3 dimensions, 3-dimensional trusses now. And I've done this, and again, people's eyes glaze over when I do this, but you can still do project, and you actually, you're now in a 4-dimensional space, and you get these 6 projections. It's just like the Maxwell electromagnetism, the 6 projections, and 3 of the projections tell you the moments, and 3 of the projections give you the forces. So that all still works there in 3 dimensions. And that's my paper that I wrote there. I didn't know that paper was still there. There it is. There. So this is the forces and the moments given by the 6 dimension, six projections, and 3 of them give you the force, and 3 of them give you the moment of this dual stress function, which these things are busy popping back into between the dual stress function and the original. And I've now got a continuum version of this. So I wrote this a couple of years ago, but I've now got a continuum version of it, which is the Maxwell one. And how can you use this? I'm nearly finished. Well, one way maybe in shells and grid shells. This is Giancarlo's PhD. He's looking in. This is what he's going to be doing his PhD on. And there's lots of fabulous work been done on this already by all the people here, Cam Miller, Toby, Arek, Bill is here and so on, and Marina. Tim Nugent, as a fourth year project, did this with me, where you look at, say, the British Museum Great Court roof is the idea, and you project it down, and you've now got 2D truss, and that 2D truss, you now do the graphic statics on the 2D truss, and you've got the forces in it, but then you pop it back up to get the roof. But to get the 2D forces, you know, put an area stress function over it. So you've now got two surfaces over the projection. So this is your area stress function, and then you pop it up and you get the roof. So there's another duality, sort of duality correspondence going on between area stress function and roof. You've got these other surfaces. And then you've got the force diagram. And this is all in the discrete case, but we can now start to think about doing this for the continuum case. It all hinges on this thing called Pusch's equation, or to the Timoshenko, it's in Timoshenko's book, some people call it the Timoshenko equation for shell theory. Careful what I say with Professor Callahan. This is one of the sort of bases for how you design these shell roofs. And you'll notice Z is the roof shape and phi is the area stress function. You can swap phi and Z, and it's still the same equation. So you can play with your area stress function, you can play with your roof space to try and design an optimal, using the applied forces to try and design the optimal thing. That's a paper. A lovely paper Cam wrote, explains how all this works from a graphic statics perspective. And there's some fantastic work going on around the world on this here. There's a Yu-Chu Chang who's doing his PhD, just finished his PhD with Mauro over in Delft, Mauro Overend. We got Toby Mitchell from SOM and Masaki Miki in Japan doing wonderful work on this with Ryan Dresser, and there's other work with Cam, Masaki, and the people in Chalmers as well. Emil Alexandra working with Chris Williams in Chalmers doing all of this here. But I will put to all of these, have you actually drawn the dual stress function? Have you really made use of the dual stress function, or have you just drawn the force diagram for it? But there's a lot of work, and that would be an extra talk. I said this was an impromptu talk, so it doesn't sort of really have an end, and this is how you can use it. But these are the directions that Giancarlo is going to go and work and do his PhD on, showing how to use the dual stress function understanding in these sorts of problems. So this is my penultimate slide. We've now got these pictures of form and force graphic statics. We've got a continuum version, and this is the Legendre transform that takes you from form to the force. So that is Euler-Bernoulli beam theory. We teach it in the second year, and have you ever seen it looking quite like that? That is a simple Euler-Bernoulli beam. And I'm going to end this lecture with the most pompous ending to any lecture you've ever heard of, ever before. This is my ending. When I was doing this, I kind of was reminded of that poem by Keats, okay? There's a poem on first looking into Chapman's Homer, and if you know it, he picks up by Homer, the Odyssey and the Iliad, the translation by Chapman. And he said, this is amazing, it's blown my mind, this is amazing. And he compares it to Cortez, the Spanish conquistador, standing on a mountain in central South America, looking out, and for the first time ever sees the Pacific Ocean. Darion's Mount, you can look this one up afterwards, and he sees the Pacific Ocean, him and all these men, and it's totally blown their minds away, because the Pacific Ocean is not just a big blue thing full of water, it's half the flaming planet. Okay, and for the first time ever, he suddenly realizes that half a planet we've been missing, guys, and it's sort of over there. And my point is, that's what I normally do, and there's been half a planet missing, which is this one. So on first looking into Maxwell's collected works, I found this whole half a world to structural engineering that we've been missing. And maybe we should think about what's over there, and maybe there is stuff there to be thought about. So I'll end there. Pompous ending. Maybe I over-egged it, but why not? Okay. Thanks.